Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amirul Amin bin Kamian. My matric number is 190087. My supervisor is TS Muhammad Fadli bin Abdurazak. So today I would like to present about my final year project, which is the title is Research Performance of Lead Acid Battery for Off-Grid Solar System. So basically this presentation include 5 chapters, which is introduction, literature review, methodology, result and discussion, and the last one is the conclusion. Okay, so the first one is the introduction. Okay, in solar system, lead acid batteries are the most popular form of battery other than lithium ion types of batteries. It have a long lifespan and low cost when compared to other battery types despite their low energy density, low efficiency and low maintenance requirement. It also have a distinct advantages of being the most widely used type of battery for the most rechargeable battery application. It has its own state of charge and depth of discharge, which is different from other types of batteries. Each element serves a purpose and can influence the off-grid solar system performance. There are two basic ways to determining the SOC, which is the terminal voltage and specific gravity. For the depth of discharge, lead acid batteries should be discharged only by 50% and to increase its life, which means that they should be cycled in the 100% to 50%. So in this research, it have four objectives. The first one is to identify the properties and capabilities lead acid type batteries on the solar system. The second one is to study the effectiveness of lead acid type batteries on solar system. The third one is to assess the level of charging and discharging of batteries using the solar system. And the last one is to comparing the differences in the analysis of lead acid batteries with lithium ion type batteries. So the scope of the project is, the first one is to learn and find information regarding the nature and capabilities of lead acid batteries if used in solar system. The second one is to study and analyze SOC, DOD, and effect of the on the battery during charge and discharge process done using solar system. And the last one is analyze the capability comparison between the lead acid type batteries and lithium ion type batteries. So this is the literature review. So they have four related previous study relate to my research. So this is the methodology. See, this is my flowchart for my research, and this is the block diagram for my research. So I will explain about the block diagram for my research. The solar panel is the responsible for soaking up the sun's ray and passing that energy on the solar charge controller. The voltage source will then be stored in a battery that is a lead acid battery through a solar charge controller. The performance characteristics of the battery, such as its state of charge and depth of discharge, will be evaluated. The next part was inverter will change the DC source to an AC source before transfer to the load. Finally, the source from the inverter will connect it to the load, which is 10-watt lamp. Okay, this is for chapter 4, which is result and discussion. Okay, to analyze this battery performance, it have three condition, which is condition A, condition B, and condition C. So the condition A is battery charging and current flow. So this is the graph for the day 1, day 3, and day 5, which is start analyzed from 9 a.m. to 6 p.m. And day 2, day 4, and day 6, I start analyze the charging voltage from 9:30 a.m. to 6:30 p.m. So for the day 1, voltage gradually increase early in the morning until 1 p.m. due to sunny weather. Voltage also decreases slightly from 1 p.m. to 2 p.m. due to sudden gloomy weather. After that, voltage slightly increase and decreases, which stated on the graph, in the afternoon due to overcast weather. So the maximum voltage input on the day 1, which is 1st January 2023, is 13.52 volt at 5 p.m. And the current pattern increases and decreases slightly while the battery is charging with the solar panel. The peak current gain from the day 1 is 1.61 ampere at 2 p.m. and the lowest current gain from January 1, which is the day 1, is 1.2 ampere at 1 p.m. For the day 3 and day 5, the data pattern is almost the same. So the first one is voltage charging on the battery increases slowly on the 3rd and 5th days. After that, the data collected from the voltage charging is almost the same on both days due to cloudy weather start from 9 a.m. to 11 p.m. Cloudy weather blocks some sunlight from reaching the surface of the solar panels. Sunlight has been scattered or absorbed by the clouds, so solar charge controller charge the battery to the regular rate between 12 p.m. and 4 p.m. The highest charging voltage on the 3rd day is 13.3 volt and on the 5th day is 13.1 volt. The pattern of current input on these days is slightly increasing and decreasing between 1.11 ampere to 1.17 ampere. Okay, this is the result and analysis for battery charging and current flow for day 2, day 4, and day 6. So on these 3 days, the data collected is start from 9:30 a.m. to 6:30 p.m. For day 2, weather on the second day was good for running charging process, clear and sunlight clearly visible starting from 9:30 a.m. And the reading of charging voltage on the battery at 9:30 a.m. was 10.8 volt and increased sharply to 12.9 volt at 10:30 a.m. Next is charging voltage on the battery slightly increases and decreases until 6 p.m. as stated on the graph. So the peak input current for the second day is 1.6 ampere. The pattern of the current on that day is slightly decreasing and increasing due to current moving along with the voltage charging. For the day 4, we can see that fourth day's weather start off overcast and stay that way until 10:30 a.m. Weather remained sunny from 11:30 a.m. until the evening, causing the voltage charge to remain consistent. So the temperature climbed at 5:30 p.m. as it was hotter than earlier. The last one for the day 4 is current input for the day does not change much and slightly decreases in the evening. So the data for day 6 is on the day 6, weather remained overcast and rainy until 1:30 p.m. The current is slightly increased from 9:30 a.m. until 12:30 p.m. and drastically increased at 2:30 p.m. As we can see, the peak current for the day 6 is 1.5 ampere. So the next analysis is for condition B, which is the discharging state of battery and the current flow. So for day 1, day 3, and day 5, the discharging start evaluate from 7 p.m. to 10 p.m. And for the day 4, day 6, for the day 2, day 4, and day 6 start evaluate from 7:30 p.m. to 10:30 p.m. For on these 3 days, which is day 1, day 3, and day 5, voltage drop pattern is almost the same for day 1 and day 3 as we can see on the graph. After that, voltage drastically decreased from 7 p.m. until 10 p.m. from 12.3 volt to 6.3 volt on day 1 and from 12.4 volt to 5.6 volt on day 3. So the discharging voltage drops slowly from 7 p.m. until 9 p.m. on day 5 and drastically decrease at 10 p.m. which is the last data for discharge. So the current output for these 3 days is slightly different. On day 1, the starting current output is set 0.07 ampere and drop over time, and the last current reading on that day is 0.035 ampere. So for day 3, the output current drops drastically compared to day 1 and day 5, which is starting at 0.084 ampere and the ending at 0.021 ampere at 10 p.m. So the environmental factors such as temperature, humidity, and other environmental factor can affect the performance of the battery, which may cause the difference in current output when the data is taken on different days. So for this part is the analysis for battery discharging and current flow for day 2, day 4, and day 6. As we can see on the graph, day 4 has the highest battery voltage value because of sunny weather during the charging phase. Day 4's voltage dropped excessively from 7:30 pm to 8:30 pm from 12.7 volt to 8.1 volt, and the dropping pattern is similar to day 2. Day 6 voltage drop linearly starting from 7:30 pm, 8:30 pm, 9:30 pm until 10:30 pm, which is 12.4 volt, 10.2 volt, 8.2 volt, and 5.3 volt for the last time. That the data shows the voltage of the battery decreases over time. So there are some differences in the voltage measurement taken on the different days. On day 2, as we can see, current was highest at 7:30 pm, which is 0.198 ampere, and decreased at later times. On day 4, current was lowest at 7:30 pm, which is 0.128 ampere, and decreased at later times. For the day 6, current was consistently higher than on day 2 and day 3 with a peak at 8:30 pm, which is 0.086 ampere. So the data suggests that the current may vary based on the time of the day and day of the week. So after that, the current output dropping pattern from 7:30 pm until 10:30 pm is slightly similar on all days. So lastly, when data is collected on consecutive days, the current output of a heavy battery may change for a reason such as a state of charge of the battery or the discharge rate. So the last part for the result and analysis is condition C, which is temperature condition on solar panel. So the first one is the temperature condition on solar panel on sunny day. So based on the graph, on day 3, weather started sunny from 9:39 am and sun was clearly visible. Temperature on solar panel increased from 2 pm from 29 degrees Celsius to 40 degrees Celsius and 41.3 degrees Celsius to 55.3 degrees Celsius. Weather temperature start to decrease at 3 pm until 6 pm as weather became dimmer, causing decrease in temperature on solar panel. So the charging voltage will be slower compared to the sunny times. Temperature of the solar panel is directly related to ambient temperature, and solar panel gets warmer when the weather is warmer and cooler when the weather is cooler. So when the sun's ray hit the solar panel, they cause the panel to heat up, and the warmer the ambient temperature, the most heat the solar panel will absorb, and the higher the panel's temperature will be. So this is the second part for the condition C, which is temperature condition on solar panel on cloudy and rainy day. So on the 6 days, as stated on the graph, weather was not conducive and into charging process, raining since early morning hours and persists throughout the day. Weather like this is not ideal for charging a battery, as the rain and clouds can block sun's ray and reduce the amount of solar energy that the panel can absorb. As a result, the charging process may be slower and less effective. So according to the data, solar panel temperature went from 41.3 degrees Celsius to 51.6 degrees Celsius, while weather temperature slightly increased from 29 degrees Celsius to 35 degrees Celsius in the first 4 hours. So weather temperature start to drop from its peak value between 12:30 p.m. and 5:30 p.m. because weather turning sunny and hotter cause temperature of solar panel to rise as well. When the ambient temperature is cooler, the solar panel will absorb less heat and its temperature will be slower. So this is the last part for my presentation, which is the part 5, conclusion. So as we can see, this is the comparison between the lithium ion battery and the lead acid battery. So as we can compare on the graph, the blue line is the lead acid battery and the red line is the lithium ion battery. So this data is collected on the same day, same system and same weather. During charging voltage, lithium-ion battery has faster charging voltage process and able to start charging earlier than lead-acid battery. They may be due to lithium-ion batteries being more sensitive to sunlight and able to start charging when sun's rays are detected, even if light is not very bright. Lithium-ion battery has higher starting voltage than lead-acid battery. So this suggests that lithium-ion battery may be more efficient and effective in charging from a solar panel system under condition tested for day one. For the discharging voltage, at 7 p.m., as we can see, voltage on lead-acid battery was slightly lower than lithium-ion battery. By 8 p.m., lead-acid battery experienced sharp drop in voltage, while lithium-ion battery's voltage only decreased slightly. By final measurement at 10 p.m., lead-acid battery had significantly lower discharging voltage than lithium-type ion battery. So in conclusion, this suggests that lithium-ion battery is most resistant to discharging process and able to maintain a higher voltage for a longer period. So it is likely that the lithium-ion battery will perform better in terms of energy efficiency and capacity, but the lead-acid battery may be a more cost-effective option in the long term. So the next part is the Gantt chart for the final year project 2. So the last part is the reference during the final year project too. So that's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh.